discussion. Good afternoon, everyone. In the next 45 minutes or so, we are going to see how we can bring in the space conditions on planet Earth and create conditions that mimic a variety of objects in space, not just the solar system bodies, but also those that are beyond our reach, the interstellar medium, the space between the two stars, and so on. So before going into the simulation part, we have to understand what are the space conditions and what is present there and what we know about it as of now. And then we go to see how we can create those conditions on planet Earth. Okay, right. So here in this screen, you see we have given two temperatures. One is 10 Kelvin and the other one is greater than 10,000 Kelvin. So by now you might be guessing, yes, we have a variety of regions in space, which can go from lowest of temperatures to high temperatures that are not present on planet Earth. Okay. Of course, no, both these temperatures are not present on planet Earth, isn't it? Right. This slide, this is the laboratory logo of astrochemistry experimental work that is carried out in PRL. So from the left, you see, we start with simple molecules, and then the molecular size grows, and we go to larger molecules. On the other side, you see, we have the planetary bodies. So it spans from here on the right top corner, you see, we have our own moon, and we have Mars, this is Pluto, this is Europa, and the other moons, this is Titan, and so on. So you can see that the conditions in the solar system, objects which you can see here, but are not limited to. And in the background, you can see the deep space, which is called the interstellar medium. So all these conditions are simulated on planet Earth, which is right here in the middle. And you see, India is here, and in the western side of India, in the western part, is where we simulate these conditions. Right, next slide. It's not moving. Okay. So before we go to space, we'll take a few minutes of what is the chemistry on planet Earth, and then we'll move about to our atmosphere, then to the moon and the other objects in the solar system, then deep into space. A few slides are from my last year's ISRO start lecture. I thought of just giving you a glimpse so that there is some connection between the lectures and why simulating space is important. So if you look at the chemistry on the surface of planet Earth, combustion is one process. So here we are very particular that without electromagnetic spectrum, we are looking at the combustion. And this you know very well. Many of you might be driving vehicles. The internal combustion engine, there's a lot of chemistry going on there, where the fossil fuel, it burns with air, and the residues are hydrocarbons, oxides of carbon, and nitrogen, and we get particulate matter as well. Okay. So when you talk about hydrocarbons or the carbon component that is coming out of this internal combustion engines, are there any allotropes of carbon that are present? I hope you all know about the allotropes of carbon, which is the graphene, fullerene, which is the C60, the football-like molecule, which you can see here in this logo here, we've got, and the carbon nanotubes and so on. Okay. So the question is, the chemistry on surface of Earth, are we looking at similar process outside Earth, in the solar system or in deep space? Okay, this is one of the questions. Next. Well, there may be some answers. So some of the astronomers, when they took spectrum, the x-axis, if you see, this is infrared. Okay, and what you're seeing here is mid infrared. Okay. They obtained some spectrum, and then that spectrum was then compared. They compared it with the auto exhaust, the internal combustion engine exhaust, and you see there is a good match. So does this mean that somebody is driving vehicles in deep space? Certainly not. But the processes are happening where the the elements and the molecules are engaging in chemical reactions, producing molecules that we know what is there on planet Earth, and there may be some molecules which we don't even know what is there. Okay, right. Next, let's move from the internal combustion engine back to what we see with our eyes. Because internal combustion engine, we cannot see, right, what is happening inside and in the inside this engine, which is driving your scooter, bus, and car, and all that. But what you can see right in front of your eyes, at home or in worship places and so on, where you can see the camphor being burnt. The moment you lit the camphor, you see a couple of centimeters of flame, and above the flame there'll be the black particles flying around. Those are carbon-based molecules, or say particulates. Okay, that's why you can see them quite easily. It's a residue. Okay, so it is also burning the carbon content. Again, the same question. If you take that one and see, will you see the allotropes of carbon, or these the same processes which are happening? We do not know, right? So we need to know, because the last slide you saw that astronomers have given some spectrum which are matching with what is happening here with the carbon-based molecules, right? Right. So here we slightly shift to another part of the chemistry, where you saw this internal combustion engine and the camphor burning, which are very, very hot. The temperatures are very hot. Okay, but here we move to the ice part of it. And when we say the ice part of it, the ice component of molecules, which means we are not on the surface. We are somewhere else where the low temperature is dominating. So we are going into the Earth's atmosphere. So when you move above, there you're going to see the morphology, which is solid, liquid, or gas. Okay, which we know. But why we are particular about the word ice here? The reason is, if you say ice, the immediate thought comes to us is like, okay, water ice, which is on the right side, you can see here, or it could be an ice cream, depends on the person who is looking at it. But when you talk about ice, with respect to molecules, and especially with molecules that are not on planet Earth, and the conditions that are very different, then the word ice refers to any molecule that is frozen. Okay, any molecule, irrespective of, if a molecule can freeze, then it is called ice. Okay, fine. So we have seen two components. The chemistry, which is happening, is at very hot temperatures, and there are places where the molecules are frozen, so we call them as ice. Okay, now move to the next one. So we are still in Earth's atmosphere, right? There are many reactions that are going in Earth's atmosphere, but we will focus on something which is very well known, the very well studied chemical reaction on Earth's atmosphere, which is of interest to many, is the formation and destruction of ozone. You may see that ozone forms only a tiny fraction of Earth's atmospheric component, but it is the molecule which is controlling many factors. So a minor component, molecule which is present in little numbers, can influence a lot on a planet's, atmospheric evolution and a lot of other factors. All right. So what is special about ozone? When there are a lot of molecules that are present on planet Earth atmosphere, ozone forms from oxygen. We have plenty of oxygen on our atmosphere, right? So ozone forms from oxygen by absorbing the UV radiation. So we are having an alternative absorber to absorb the ultraviolet. Otherwise, our DNA will be absorbing this ozone, the ultraviolet radiation. Okay, so ozone is helping us. So here you should note that when we say ultraviolet, which is the wavelength, say for example from 320 nanometers to 220 nanometer and so on, but here we're given to 40 to 300, so you can slightly extend it as well. It's not a problem. Okay, ultraviolet is known to have 3 sections, A, B, and C. So the ultraviolet absorber ozone is helping us. But what about the same molecule when it is present on the other objects in the solar system? And the first question is, do we have ozone which is present on the other objects of our solar system? Because one has to find that, right? So here the question is, when you talk about simulating space, it's not like only you're bringing in the condition. Before you bring in the condition, you need to know what is the condition there. For example, if you take moon has no atmosphere. Moon we can easily study. Okay, if you go further away from the Earth, away from the sun, then you're looking at conditions which are studied to some extent by the spacecrafts, but which are studied in depth using the telescopes under the whatever the limitations we have by looking at the telescopic via the telescopes. So the conditions that we know are only through observations. The moment you go much farther away from Earth, okay, and especially if you look at the clouds, the stars, or the dark spaces between the stars, we depend only on the telescopic observations. We are unable to send spacecrafts there, right? So here's the ultraviolet. The wavelength matters in the ultraviolet, but in the Earth's atmosphere, it is not just the ultraviolet which is reaching. The sun is throwing out photons, of course, almost in every wavelength. So here we have to consider one more, which is called the vacuum ultraviolet. So what is the vacuum ultraviolet? The wavelength which is below the ultraviolet. So say, for example, from 220 nanometer up to 1 nanometer. Okay, it's a quite large wavelength, up to 220 nanometer difference you can have, but we can separate them into different sections and how the molecules will respond to these different wavelengths. But the moment you go to 1 nanometer and so on, that is where the X-rays come to play. Okay, so you can see that our atmosphere is stopping most of the photons, including the ultraviolet, and then helping us to survive here. Okay, so the question is it good to have an atmosphere? Certainly, yes, it helps in many ways. But it's not that every solar system object has an atmosphere. So we are having places where there are no atmosphere. That is, I shouldn't say that. Okay, let us talk about the word exosphere also here. So what is the difference between atmosphere and exosphere? Atmosphere is a place where the molecules present in the gas phase above the surface of a planet, they collide quite often. Okay, the space between them, the distance between the two molecules are of the order of a few micron. But if you talk about an exosphere, for example, if you take our moon, that is why the astronauts go with the astronaut suit and all that, so that they have enough air within the suit to breathe, because moon doesn't have atmosphere. Rather, we call that as an exosphere. The reason is the space between the distance between two molecules are quite large, and it takes such a long time for them to collide. So you can see for a small space of one centimeter cube, there'll be hardly a few molecules. So they don't meet each other that often. Okay, so that's the difference between an atmosphere and an exosphere, right? So when there is no atmosphere, the absorption of photons are not going to happen. So in that case, we are going to have a lot of new players that are happening, that are going to induce the chemical changes. And the new player here are the electrons, mostly the secondary electrons, which are coming out of molecules. When these photons or X-rays infract the molecule, we can expect that the molecules get ionized, and we are looking at electrons that are coming up. Right. Now we have gone above the atmosphere. Now we have gone to the moon, because moon is our nearest neighbor. So we have to have a good understanding of our neighbor, right? So I told about the exosphere, right? So the exosphere molecules themselves are not meeting each other. They're not colliding. So certainly the interaction with the atomic the particles coming from the sun and the photon, the interaction is going to be very less, which means all these photons are going to reach the surface and the particles also will reach the surface. For example, one of the findings from Chandrayaan-1, the presence of water molecule almost all over the moon. The reason is behind the chemistry that is happening where OH radicals are being made. Hydrogen is available in plenty and they combine to have water, and this water will hop around and go to the cold traps. That's where you can see a lot of water being present. Right. So we looked at a few things. Now we are going to see a slightly unusual thing. Even though it does not have an atmosphere, moon does not have an atmosphere, it has an exosphere. It has places where it can accumulate the molecules. And these places are the cryogenic traps. But the temperatures are very, very low. Okay. So the molecule has the ability to stay on the surface. It has enough energy to bind to the surface when the temperatures are low, to an extent that the vapor pressure of the molecules are very minimal, so they don't go off the surface, right? So when you talk about the places which are very cold, how are these places present on the moon? Is it an artificial thing or is it a natural thing? Of course it's a natural thing, because of in the previous talk you heard on Mars there's a lot of craters and so on. In the previous other sessions also you would have known about the craters on the moon. So if you look at the craters which are on the poles, especially on the South Pole, these craters are deep enough that the sunlight does not fall. The moment sunlight does not fall on these craters, there is not going to be any energy source to heat the surface. So the temperature is going to be low eventually. This is what you must have studied in your school and in your school time, mostly at the end of the school time, that the background radiation is 2.7 Kelvin. Unless there's an energy source, so if you have an object in space, the temperature is going to slowly, gradually fall down to a low temperature. So the same case here, when the crater, even though it's present on the lunar surface, is not receiving any photons from the sun, the temperature is going to fall. So these are the places where the molecules find a trap where they bind to the surface or to the other molecules and make an icy layer. So is this the only place? No. So far from the research what that are carried out using spacecrafts to understand the craters on the moon, it turned out that many permanently shadowed craters are present on the lunar surface. So this is just one example. There are even more studies that show the spectrum that are taken from these permanently shadowed craters. So most of the permanently shadowed craters are harboring a lot of water ice. Okay, so what you see here is not the colors. The blue colors are not real ices, so don't think that this is the ice that you're seeing. It's just to show that these are the craters where the molecules are frozen, especially the water molecules are frozen. Okay. So there'll be a question you might ask, well, if there is ice, then we would be able to see it. Okay, but there is a problem. Say, for example, if you take 2 plates and keep it in the fridge at home, and if you take a plate after 10 days, a metal plate, for 10 days, you'll be able to see that ice is formed on the surface because your eyes are able to see them. But you keep another metal plate and take it out in just half an hour, like 15 minutes to half an hour, and you take the plate out. And if I ask you the question, is there water ice on this plate? You would definitely say no, because you won't see anything, right? But if you carefully look into the physics, the plates, both the plates get colder, right? But the plate which you take after 10 days keeps on accumulating the water molecules on the surface, building the ice. So the ice is quite thick. It is building the layers. The ice is quite thick that we can see. But the other plate, which is also getting colder within that 15 to 30 minutes, where there are molecules of water on the surface forming the ice layer, but beyond the detection limit. The same plate, if you take to any of the spectroscopy technique, it will show you, okay, water ice is present. Similar way, the spacecrafts couldn't see bulk of water ice inside these craters, but the spectroscopic signatures clearly pointed out that yes, definitely there are frozen molecules inside these craters, especially water ice. Okay? So when you say spectroscopy, again it opens up the electromagnetic spectrum, where the wavelength range can be used in different ways to understand what is present on the planetary bodies. And you have come across 1 or 2 of these wavelengths, which we will be discussing in this talk. Right. So now we are on the chemistry on the surface of our moon. This has some relation to what you have seen on planet Earth. For example, you know the chemical that is present in the soda that you have seen, carbonic acid. It's a product of water and CO2. So we know plenty of water is there on the surface of our moon and in the other solar system objects. Plenty in the sense, not don't take it in relative ways to planet Earth, okay? In relative ways of other molecules, okay? What is there, okay, in good amounts. And carbon dioxide is also known. Carbon dioxide is also present along with water in some parts of it. So the moment these 2 molecules react, then they are going to make carbonic acid, which is the one which you see in your soda and so on, okay? Right. So what is initiating this chemistry? So there should be some energy, right? Without energy, chemistry won't happen. For example, the same thing is there on planet Mars as well. For example, the same carbonic acid is there on planet Mars as well, because Mars has contains a lot of water and CO2. You must have heard from the other talks, right, about Mars. Right. So we know that this molecule is the major product when you have water and CO2, but you'll be surprised to note that to date we do not have a confirmation that this molecule is present, because the spectroscopic signatures are to be present. Only then you say, yes, this molecule is present. The chemistry says it is there, but our observations of Moon and Mars and other places, we could not confirm that carbonic acid is present. Okay, so you see that the conditions that we simulate, the space conditions we simulate on planet Earth, throws back something which must be there. But what our understanding of those places so far does not tell us that, oh well, it is there. Okay, so there is some complexity, not just the molecular complexity in our scouting the information that we need from the other places. Right. Now slightly move out of Moon, we'll go to the Martian system. Well, Mars has plenty of carbon dioxide, and if carbon dioxide is present, chemistry dictates that you also get ozone. Definitely, yes, ozone is detected on Mars. This is not at all a problem. So there is ozone on another planet other than Earth, right? So on planet Earth, it is thought that ozone is a biomarker. Because of ozone, we get the flora and fauna, as ozone stops the ultraviolet and so on. But here is the case where ozone is made completely from chemical reaction, starting from carbon dioxide. Okay, right. Now we are moving away from Earth towards Mars, right? But now we move towards the Sun. You'll be surprised to note that there are places very close to the Sun, especially on planet Mercury. Of course, on planet Mercury, there is no other place than Mercury close to Sun. If you look at the poles of planet Mercury, again, similar to our moon, there are craters which are not exposed to the sunlight. Okay, so again, wherever there's no sunlight, the temperature is going to fall. Then the temperature is going to fall, it is going to act as a cold trap, and molecules are going to be accumulated there. So there are places even close to the sun that can have molecular ices. Right, nice. That is one understanding, that we have understood the similar places from close to the sun and away from the sun. Okay, so one example you can take, if you're unable to go to Pluto, then you can study the permanently shadowed regions on Mars or on Mercury. So they are a bit of analogs of the colder places in the solar system. Right. So we can talk about many of the solar system objects. So that's why you have separate lectures about these objects. Here we have listed a few of the moons of Jupiter and Saturn. And not, of course, not many moons of Neptune or Pluto, but the few moons of Jupiter, Saturn, and the Neptune and Pluto also, you see, they have a common molecule, which is mostly water. And there is a bit of SO2 in a few of those, nitrogen when you move out of the solar system. So you can see the difference going up. I should have put an arrow here so that we are moving away, right, from the Jupiter to the Saturn, Neptune, Pluto. But if you carefully see, when you move away from the sun to the distant edges of the solar system, nitrogen comes into picture. Okay, and if you're in between these places, Jupiter and Neptune and Pluto, you can see that ammonia has some role. And that's where ammonia starts to kick in. So you can see, when you say that we are simulating the conditions of the space conditions, it's not going to be the same for even for the solar system objects. Then imagine what about the deep space? It's going to be quite difficult because the chemical inventory is quite wide. It's not that simple, right? Okay. The satellites of Jupiter and Saturn. If you look at these are few examples only. Okay, it's not the complete list. If you look at the satellites, you just take a look at all these very carefully. On the left, you have the satellites of Jupiter, and what we're given is the satellites of Saturn, Rhea and Dione. The next slide, these ones looks like satellites because there is no interactive sessions possible right now, but so I will give you the answer. These ones look like the satellites. Okay, what you saw here in the previous in this slide, but these are not satellites. These are the underside of the frying pans that are used at home. I took it from one of the sources, anonymous sources. That's why I couldn't acknowledge it here. So they appear to be the satellites, but they are not. Rather, they are the underside of the frying pans. And why there is a difference in color? It's because of the chemicals, the masalas that you use in your cooking. So the chemical composition that you have seen are going to be very different, which means there is someone who is bringing these colors to the moons, which means the chemical diversity. Okay, and given the size of the moons, the size of the objects, and so on, you're looking at a painter who's very, very, the size is massive, and that is none other than the magnetosphere of the giant planets. The giant planet magnetosphere here is the one from Jupiter. The magnetosphere of the giant planet, okay, that is responsible in transferring the elements or the molecules from one moon of Jupiter to the other. The same thing happens for Saturn as well. I don't want to go deep into this. Right. So what they do, the magnetosphere as a plasma bombardment, they pick up the molecules and then it injects into the neutral clouds. And we have the ionization kicking in because of these photons. The moment you get an ionized molecules, the magnetosphere will pick it up and it can now take it to the far edges of its own planetary system. Right. So we have seen the different places. We have seen we've seen the source. We know what is going on in individual systems. And now, when this energetic particle, which is taken by a magnetosphere, when it hits the surface, okay, in general, you take a surface, okay, what happens? It is capable of producing secondary electrons, which you see here, and it's capable of producing the moment you have the secondary electrons, which means the molecules are ionized, and we have excited atoms and molecules until the energetic particles comes to a rest. It is making a lot of damage to the surface. So this is where we get the energy to start a chemical reaction. The moment you have an electron, secondary electron, or you have an ion and so on, chemical reactions are going to start. Right. As I said, the same for the Jupiter system, we have a magnetosphere and so on initiating it. The same is for the Saturnian system. And what you see here, this is the Saturn, it's just a pictorial. And on the edge of it here, this is Titan. Okay. And this is Rhea, one of the moons. This is Dione. This is Dione. This is Rhea. This is Dione. Tethys and so on. But you see the element, the plasma environment around the moons are different because Titan has a lot of nitrogen. So it contains a lot of the nitrogen tolerance is more. Whereas the places close to Rhea and Dione are rich in oxygen. Okay. Oxygen atoms are the oxygen ions. You see that, it is very diverse. Right. This is not a Photoshop image. It's a real image of the Saturnian system taken by the Cassini spacecraft. You see on the right here, this is Rhea, one of the moons of Saturn, Rhea, and behind this is where Saturn lies, and these are the other moons, and these are the Saturnian rings. Right. Why I was like showing that? So for Rhea, if you take as a molecule, the surface of Rhea has molecule which is used in the rocket fuel, hydrazine. Okay. So it is thought that this molecule would have either have transferred from Titan over a long time period, the geological time scale, or whatever the ingredient that was there on present on Rhea, that would have been chemically changed by the ions and photons that are hitting the surface of Rhea. Okay, and you see the distance between these two moons are the order of, it's twice the distance between our Earth and our moon. Okay, it's not just that. If you go to the Jovian system has 4 larger moons, of which to date we know that 3 moons contains ozone, has ozone on the surface. For example, this one moon, Callisto, which has ozone on the surface. The band in green color that you see, this is the ozone reduction band. The band in blue, what you see, is the sulfur dioxide. Okay, so the moment sulfur dioxide is present, like CO2 giving ozone, instead of C, you replace that with S, sulfur dioxide. SO2 can also produce, can also synthesize ozone. Okay, so we have seen that the molecules on the surface of the icy objects in the solar system, for example, with the Rhea or the Callisto, 2 or so on, they can be studied. We can understand, okay, it's present there or not using the spectroscopic techniques. Okay, and here you see the x-axis, it is in wavelength. For example, the other one we discussed, the auto suit, that is in wave number, which is the infrared. Okay, so you're looking at the infrared and the ultraviolet, and we have also slightly touched on the vacuum ultraviolet, right, where the wavelength is from 1 nanometer to 220 nanometers, and beyond that is very ultraviolet, right? So we saw the permanently shadowed craters on the moon, correct? And in your other lectures, you have seen that, you know, craters are being made. Thing comes at a very high velocity, comes and impacts on the surface. So the craters are being made, right? So if you want to simulate the conditions of space, you also have to consider the impacts as well, isn't it? So within this 45 minutes, we won't be able to cover the impacts part, but we will cover the other simulation. So the impacts, I'm trying to play this video. Stay with me. Yeah, you can see that. Okay, whatever happened right in front of your eyes now, this damage is because of 2 mm bolide, which was hitting the target there at a velocity of 5 kilometers per second. Okay, so the craters you see here, these were formed by objects which are of massive sizes, because you are looking at a few kilometer size craters, right? Massive sizes coming at a velocity more than 15 kilometers per second or 20 kilometers per second, and they hit, and that's where you have this physical damage. In addition, chemical damage is also there. So when you simulate the conditions in solar system, so you have to also consider, you know, macro-sized objects, not just the electrons, photons, and X-ray, or the ions, and so on. Okay, right. Go to the Pluto system before we move into the major part. Right. So I pointed you in the other slide that the moment you go out or away from the sun, much closer to the edge of the solar system, you got nitrogen into the play. Okay, and then you see the system, Pluto system here. We have Pluto and Charon. They have some sort of similarity, the brownish color and so on, which is kicking in. Right. So there is a need to understand what are these chemicals that are giving this colorant. The same we saw there for the Jovian and the Saturnian system, where the magnetosphere is acting as a painter, right? But here for the Pluto system, we don't have the sort of magnetosphere what we see for Jupiter and Saturn. So we have something else which is playing the role. Let it be the cosmic rays or the sun photons and so on, right? Which means the chemical reactions are happening almost in every edge of the solar system, whether you have an atmosphere or not. Everywhere it's happening. And how you understand the chemical reaction, you have to do that. You have to do the reaction yourself and then understand. But what we know so far, if you talk about a chemical reaction with respect to temperature, the rate of the reaction can be equated to the temperature. That's what Arrhenius equation says. This, you know, most of you know very well. I don't have to explain that part. But the question we put to you is that what happens when the temperature is very low? What happens to the Arrhenius equation? This you can look at, right? And you're all lucky. In your lifetime, you are able to see one of the distant objects in the solar system. The image from the left is from the New Horizons. It's called Ultima Thule, or the other name was Orokoth. They found that the pristine objects in the solar system do exist, but in the ice form. So most of this is ice, and the colorant on the top is what we need to understand why this coloring comes. Okay, so you cannot have a sample of Ultima Thule, or you cannot send 1 or 2 other spacecrafts to this to study, because it takes nearly 8 years to go, 8 to 9 years to go. So the best thing is to bring this condition to the planet Earth and then study. Okay, right. So we have to examine again what are the components that are present on the surface of Ultima Thule, which is giving it this sort of a color, and is there anything interesting? Right, just summarizing. So if you move away from Earth, except for Mercury, if you move away from Earth, the temperature is going to go low. The permanently shadowed craters on planet Mercury. Okay, those are also places where the temperature is low. If you move away from Earth, you're definitely going to a place where it is very, very cold. But it is something hidden, which in your school textbooks, you have all come across this equation PV equals nRT. This is what governs the temperature and the density in deep space. Okay, so these are the places where you can get, or where you can, where you can get a variety of chemicals that are present, the molecules, variety of molecules that are present. So the average temperature, I forgot to mention, if you look at the Jovian system, the average temperature of the moons in the Jovian system are of the order of around 100 Kelvin or something. For the Saturnian system, again, it depends on what sort of moon that we are looking at, and the temperature is going to go down. Okay, so the average temperature is what we see because there is a day and night cycle and so on. So for here, for the dense molecular cloud, 10 Kelvin, okay, you can say the units are given on the top. So if you work it out, you will get the numbers that are there in the ISM. So you can see that you have studied astrochemistry, but we didn't specifically look for it. Okay, right. So when the density is very, very low, it's not that it's like an exosphere again, where the reactions cannot happen that fast. So we need certain players for the reactions to be much faster. Okay, from here I'll take another 10 minutes. We will be finishing. Right. So you have seen that the chemistry is always happening everywhere, and the chemistry can be in the gas phase or the solid phase. And in this lecture, we are going to talk about the solid phase. We are not going to look into the gas phase. Okay. Solid phase, when you say solid phase, is not just the ice, but is the dust as well. Okay. So the dust from the comet and so on, no? But by simulating the the space conditions or so, you always get a residue. Okay. And this dust, when you say these are the order of few micrometers or a few hundreds of nanometer or tens of nanometer, not bigger than that. That is the place. So this dust will act as a core, and your density is very, very less. What you do, instead of having reactions happening quite rarely, this dust will act as a place where the molecules can stick together like your cold trap, what you have discussed a few slides back in the moon, surface of moon or so on. But here the size is very, very small. They're of the order of a few microns or a few tens of nanometer. When the molecules accumulate, they react, and then they go off the surface. So this is how is an accelerated process where the molecules, new molecules are easily being made. Example, you see here the accretion, and then they diffuse, they react, and then they go off. Okay, right. Here's the abundance that is given for the elements. These are not for the molecules. Okay, fine. Now, when you talk about formation of new molecules, that the dust grain is helping to form new molecules. So what are the molecules that are known to date or that are discovered so far? Okay, it's not that what is discovered only are present. There are plenty that are present, but we are able to only locate a few, but not all of it. Right. So until 2010, you can see the growth. These are all the y-axis on your the y-axis is a cumulative number. It is not that every year they find this money. No, it's an adding. It's an added up number. Okay. So around the human landing on the moon, that's the same year when water was discovered deep in space. Okay. And then we all know carbon dioxide is there in plenty in the solar system, but only around 1990s we had the discovery of carbon dioxide. Then the laughing gas comes after that, and we had benzene quite later. And the most interesting part is nitrogen and oxygen, which we know are there in plenty on planet Earth. Even it is known to be in the deep space, and the discovery came at a later date. So this shows you that the techniques that we use are going to be quite critical in identifying the molecules. Okay, here in this plot, we have shown you that around in the year 2010, the largest molecule in the ISM, to date, we know the largest molecule in ISM is C70, which is a form of fullerene. Okay, and I've marked benzene here because you need benzene to make this. This is what we have thought so far, or at least the ring structure has to be present. Okay, right. So this list shows you that we have plenty to simulate and understand what is happening. So we should be in a position to wisely choose a few because our resources are limited, right? Right. So when we are in that process, the year 2021, which is the year just after our COVID lockdown, in the year 2021, they've discovered, astronomers discovered 41 new molecules. To date, it is the highest finding so far. So I didn't even plot any of 2010. I shall do a different plot maybe on some time. Right, you see that way we have plenty to do. But when you come back to our solar system, again, we have the same complexity. If you take comets, the number of molecules that are found on comets are plenty. And again, around 2015, I put a star here because this is the time where spacecraft went to the comet, they landed, and they looked at molecules in a much better precision than before. So that was a time, exactly 8 years before, we were able to separate whether it's the signal is from nitrogen or carbon monoxide using a mass spectrometer. So such a high accuracy mass spectrometers were even flown on spacecrafts to study comets in situ. Okay, right. So we know plenty of molecules are there. Now the question is, well, what about the classification of molecule? Whether it is a simple molecule or a complex molecule, that is the question. So if you take or the same question is applied to planet Earth, yes, we can sometimes, easily say small molecules are simple and large molecules are complex. Like what methane, water, methane, or ammonia, and so on are simple molecule, we can say. But the moment you go beyond Earth, okay, or even beyond the solar system, a small molecule is not necessarily a simple molecule, okay, or even alternatively, it can be a complex molecule as well. For example, you see here HOCN. Okay, there is a new finding, HOCS. It's a 10 days before. It's a new molecule is discovered. It's a protonated carbonyl sulfide. Okay, so you can see this molecule having 4 atoms, but all 4 are different atoms. Okay. So the question lies whether it is simple or complex. We don't know. Right. So now we have seen different cases, the conditions and so on. Let us go to the laboratory. I'll finish another 5 minutes. So there are 2 things where we have to simulate. One is the low temperature ice part, and the other is the high temperature part, where it is from the impact event or so. But in the interstellar clouds, there are events where the shock formation happens. So we are not going too much into that. We will limit ourselves to the ice part and the impacts. Okay, where the impacts that are creating the craters. Right. So first we'll see the low temperature. And the first we see the low temperature. So to the left, you see here, this were given ice. So you have to first understand what is there on the planetary surface. You have to use the spectroscopy, the techniques, infrared or UV and so on. Okay, terahertz is used beyond the solar system to study what is present there. And of course, it's now applied to the clouds of Venus and a few other places in the solar system. The moment you talk about ice, you're also talking about a bit of dust in it because this ice makes some dust. Okay, right. So that takes us to the dust part. So we started with the ice. Okay, but the moment you talk about the dust, it drags us into the high temperature part. Okay, because it's the dust which is what is going to accelerate and is going to hit on the surfaces of planetary bodies, and that's where you have this physical damages being happening. And at the same time, when this dust aggregates and they are like larger objects of size of a meter or a few tens of meter, the damage is going to be more. But anyway, we limit ourselves to the nanometer or micrometer dust, right? So all of these is some way synthesized, and there is a destruction process as well, whether it be the destruction from the electron, proton, or photon, or be the impact process. And if we talk about an atom, Yes, carbon is at the center of it because many molecules of made of carbon are being discovered. Let be the graphene or hydrogen contain graphene, the sheets of the rings of carbon surrounded by hydrogen and so on. It's called the polycyclic aromatic hydrocarbon. Okay, so we are having a you are having a plethora of problems to address. First, let me find what is there in the ice, then what sort of chemistry it undergoes and what it leaves. This residue would have gone to a dust, and what sort of new molecules can be synthesized on this surface, or with the dust gets there's a destruction of this dust, or there's be etching of this dust. When you talk about dust, it can be a mineral also, and it keeps on going, right? But what we eventually are trying to address here by synthesizing the space, by simulating the space condition, is that we're trying to understand how life originated. Okay, that is where everything is targeted. I'll skip this slide, but this is what we use to understand the chemical reactions in space, because it's not just because of electrons or protons, or not the ions, or not just the VUV, the impacts of the shock wave. The impacts do associate, they do come with the shock wave, right? So they are like interlinked. It is a combination of almost all of these. So you need to understand what is happening among these energetic sources, and when it and what sort of outcome we get if a surface, when it processes the icy surface, okay, or even a normal surface which is normal in the sense a bit of high temperatures. For example, the surface of Mercury, you can say most parts except the permutation indicators are very hot, right? So the chemicals that are brought, the temperature is cold or hot, is going to be very, very different. Right, I skip that part. No, I shouldn't skip this part. I'm sorry. So if you go to PRL website and look for acid astrochemical ISS database, you will see that the spectrum that we obtain from our lab experiments that are being loaded here for different molecules. So you can go and easily see. So you don't have to plot the spectrum. You can directly go and see the JPG files. We have given the JPG, right? So you can look for spectrum, the vacuum ultraviolet and the infrared. Okay. Right. So the low temperature part. What you see here is one example of the system where we bring in the conditions. Okay, so what you see in the middle of the system is a copper holder. That is where we bring in the low temperature surfaces. Okay, and on the left you see an electron gun, the energetic source to process the molecules. On the top is where the low temperature, the heat is to be removed from this point, right? So that is where the I'm going to show this part in detail to you in the next few slides. Okay, the cold air comes from there where the helium will remove the heat from this place, and the entire thing has to be in ultra high vacuum. So what is ultra high vacuum? The pressures which are 10 to the minus 7 millibar and lower. So the pressure which is more than 10 to the minus, more in the sense the higher numbers, okay, more than 10 to the minus 7 millibar and so on, is the ultra high vacuum. Okay, the pressure which is lower than that, 10 to minus 6 or minus 5 millibar, they are known as high vacuum. Okay, so we prefer to have it in ultra high vacuum. Okay, the reason is that number of molecules inside are going to be very less, and whatever you're going to simulate is going to be the molecule that is of interest rather than the contamination. And you see this outer chamber, what is there, this is made up of stainless steel. Okay, the outgassing from stainless steel is very less when you keep on evacuating the molecules inside. Otherwise, in the place of this, if you use some other material, for example, if you even use wood, it starts outgassing. So you get very hard to achieve good vacuum conditions. So that is why stainless steel is used. This copper here, this is the oxygen-free and high conductivity copper, so that you don't have enough oxygen there, which keeps outgassing. So these are all compatible, ultra high vacuum compatible components. Okay, we'll see them in detail in the coming slides, but it is this place at the center of this chamber where you bring the dust, which is the dust which you get in the deep space condition. I've shown you few slides back. On top of this dust, you can have this. Then the dust is cold, the molecules can stick there, and the dust becomes a tiny chemical reactor. Okay, so you can simulate that. Not just the dust. This is Europa, the planetary object, one of the planetary object, the Jovian moon, or even the permanently shadowed crater of Mercury. You can simulate. Not just that. In fact, the cometary conditions you can bring. Even the Martian conditions can be studied to some extent. But one thing is in common here. We are looking at the molecules. Molecules is what are going to be common. That particular portion, what you saw there, I've just enlarged it here on the right. So this is called the cold finger, okay? And the yellow portion, the yellow window behind this blue circle, this is the substrate. And this substrate is what is your dust here, okay? Because something has to hold your molecular ice, right? So there's the dust. Fine. And then when the moment this is cooled down, this is the oxygen-free high conductivity copper. The moment you cool it using helium, the substrate becomes cold. The moment surface is cold, molecules that are roaming around, when they hit the surface, they start forming the icy layers, right? Right. But now the substrate, hello.
We have to conclude since we are running out of time.
Yeah. I'm in the last few slides. I'm concluding. Oh. Yeah. Let me just share again. Full screen? No. Full screen now, right?
Yes.
Yeah. Okay. So the substrate, what you see there, okay, these are made of different materials: zinc selenide, potassium bromide, calcium fluoride, magnesium fluoride, lithium fluoride, and so on. The reason is some of them are infrared transparent, some of them are UV transparent, or the vacuum ultraviolet transparent. Okay, right. So the material is there, the substrate is there, and you have to pass in these molecules to the chamber inside, right? So for that you use a system of liquid holder or the gas holder through some regulators, which is used to pass in the high purity gases. You can see the schematic here, right? From the gas bottle or so, you have to mix them in some place according to the mixtures, the gas mixtures or the liquid mixtures you want. Then you pass on that vapor to the system where you want to study them. Here's the step of it. Just 3 more slides, I'm finishing. Okay, here's the step of it. That's what this is the chamber that you can use. And at this point is where your surface of an icy object comes into picture, right? And then the moment you make the ice and then use the IR source, you can probe what is going on at this place. So when you inject some sample, your IR spectrum will tell what sample you have injected and whether it is pure or not. Okay. Of course, you know what sample you have injected there, and you heat it up. You've gone to the gas phase. Your experiment is more or less over. So simple way: take a substrate, cool it down, and you inject the molecule. You make an ice. Right? With the infrared detection, you know when the number of molecules are less, the signal intensity is less, and your thickness is more, your intensity is going to grow in the infrared. The same thing, what you see here, and then you have an energetic source which is processing your surface. Now, if this energetic source is electron, it is going to go through the ice. It's going to hit your window. Your ice is completely processed. The same thing is a UV photon. You have to pass through the whole thing because UV photons are absorbed in the ice. Whatever is not absorbed, it just passes through. So it's a wavelength dependent. And then the ion, depending on the energy of the ion, most of the ions are stored in the ice. So you see the difference in chemistry. This is what is happening on the icy objects. Okay. The moment your ions are of high energy, they again pass through the entire molecular system and then get stops at the substrate. This is how you simulate it at the low temperature. High temperature, we use a shock tube. I don't have to go more into this. I don't have much time, but a shock tube is where you simulate the impacts, the shocks that are coming from an impact event. We can discuss about this in a separate talk. Right, what we did, we took some sample, which is the amino acid, and shocked it, which goes to 7000 Kelvin in 2 milliseconds, and we get some things like this. I told you, the origin of life and so on. This is done because we need to understand that how the molecules of life and the biomolecules, which is amino acids, are made in space conditions. Okay, and From the samples that we get, the meteorites and so on, people are trying to identify the amino acids. Of course, they've identified many tens of amino acids in the meteorites. But the question is how they assemble together to make the first cell. And that's where everything started. Okay, so that is the biggest question that we have, and simulating space condition inside the laboratory will help us know the answer or something closer to the answer. Stop here. Thank you.